Have you ever wondered if there's a secret dictionary that could, translate between the most disconnected parts of math? Well, today we're diving into one of the most profound ideas ever conceived, the Langlands Program. To get a feel for this, just imagine for a second, what if you found out that the laws of music and the laws of gravity were actually secretly the same thing? It sounds totally impossible, right? A hidden connection between two completely unrelated worlds. But in the world of mathematics, this isn't just some fantasy. It's the very core of a revolutionary idea. And get this grand vision didn't start with some massive formal book. Nope. It all began back in 1967 with a handwritten 17-page letter from a young mathematician named Robert Langlands. What's so amazing is just how humble it all was. Langlands sent his letter to an absolute giant in the field, Andre Weil, and basically said, hey, this is just pure speculation, so feel free to just throw this out. He even said a wastebasket was handy. But Weil didn't throw it out. He saw the genius in it, passed the letter around, and kicked off a quest that has captivated mathematicians for more than 50 years. So what is the Langlands Program, really? The best way to wrap your head around it is to think of it like a mathematical Rosetta Stone. It claims that there are hidden, direct translations between completely different mathematical universes. This lets us solve impossible problems in one world by just looking at their reflection in another one. It's a wild idea. Okay, so let's explore the first of these worlds. This is the world of arithmetic, and it's built from the most fundamental things in all of math: prime numbers. Picture this world as being kind of chunky, discrete, and honestly, a little chaotic on the surface. This is the home of number theory, where everything is built from these indivisible little atoms of arithmetic, the primes. So the key players here are the primes themselves, obviously, but also the rules that control them. These rules are described by these amazing things called Gualo groups, which capture the deep, hidden symmetries of equations. And for every single prime, there's a unique piece of data called the Frobenius element. Think of it like a specific ID number or a fingerprint that tells you exactly how that prime behaves. You're going to want to remember that name. All right, now let's jump over to the other universe in our story. If the first world was built from clunky, separate blocks, this one is all about smooth, continuous, flowing waves. This is the realm of analysis. So this is the world of harmonic analysis. It's all about breaking down really complex things, like a musical chord, into their simplest, purest sound waves. It's a world that's just full of elegance, smoothness, and incredible symmetry. The objects here are totally different. We've got these incredibly symmetric functions called automorphic forms. You can think of them as these perfectly pure fundamental wave shapes, like musical overtones. And when we analyze these waves, we pull out specific measurements, a kind of spectral data called Hecke eigenvalues. Okay, so we have two completely different worlds. One is all about chunky, discrete prime numbers, and the other is about smooth, continuous waves. How on earth could they possibly be connected? I mean, let's just put them side by side. On one hand, you have arithmetic, discrete, seemingly random, all about primes and their hidden rules. On the other hand, you have analysis, continuous, beautiful, all about waves and their perfect symmetries. They really do seem like total opposites. And this is the heart of the Langlands conjecture. It says there's a dictionary, a perfect one-to-one mapping. Remember that fingerprint of a prime number, the Frobenius element from the arithmetic side? The conjecture says it corresponds exactly to the spectral data, the Hecke eigenvalues from the analysis side. It means the two worlds aren't just related. The Langlands program is saying there are two different languages describing the exact same underlying reality. Okay, so this is a really beautiful, abstract idea. But you have to ask, does it have any real power? The answer is absolutely. This way of thinking provided the key to solving one of the most legendary problems in the entire history of mathematics. Yeah, we're talking about Fermat's last theorem, a simple-looking little equation that had stumped the greatest minds on the planet for over 350 years, and it was the Langlands philosophy that finally cracked it. So the proof is basically this brilliant detective story. Stick with me here. Step 1. You just assume a solution to Fermat's equation does exist. Step 2, if that's true, it creates this really bizarre mathematical object called a Frey curve. Now, for a long time, everyone thought this curve was way too weird to fit into that elegant, orderly world of waves. But then, and this is the genius move, Andrew Wiles proved that if the Langlands philosophy is right, then every such curve must belong to the world of waves. Boom. You got an impossible contradiction. The only way out is if the original assumption was wrong, so no solution can possibly exist. At the very heart of this massive proof was this incredibly simple but profound equation, r equals t. R was a structure straight out of the world of primes, pure arithmetic. T was a structure from the world of waves, all analysis. By proving they were identical, Wiles gave this stunning confirmation of the whole Langlands idea. And this wasn't just about solving one old problem. It was a massive proof of concept. It showed that this mathematical Rosetta Stone wasn't just a pretty idea. It was a real, powerful tool that could literally solve the unsolvable. But you know what? The story doesn't end there. Not even close. Mathematicians started to wonder, what if this Rosetta Stone could translate more than just numbers? In the last few decades, the program has exploded into geometry, and it's revealing a unity that goes even deeper than anyone first imagined, connecting all the way to the world of physics. So they developed a geometric version of the program, and this time, instead of the world of prime numbers, they used the world of geometric shapes, like, for instance, counting all the different ways you can draw loops on the surface of a donut. And just recently, in 2024, a team of mathematicians dropped an over 800-page paper proving a major part of this geometric idea. I mean, 800 pages. This just shows you how active and important this whole frontier of research still is. And here, right here, is the most mind-blowing part of all. Physicists started looking at this stuff and realized that the mathematical symmetries inside the geometric Langlands program looked eerily familiar. They looked like the exact same kinds of dualities that pop up in quantum field theory. A deep symmetry in the math, for instance, perfectly mirrors the physical duality between electricity and magnetism. All of a sudden, this incredibly abstract math wasn't just connecting ideas anymore. It looked like it was actually describing the fundamental structure of our universe. Which leaves us with one last massive question. The Langlands program showed us a hidden unity, a secret bridge connecting the very foundations of mathematics. So, if that hidden unity also mirrors the fundamental laws of physics, what does that say about the very nature of reality itself?